Okay, so I guess let's get started. Are there any questions? Okay, so I guess let's get started then. So last time we were discussing highly resolved, or DNS, sort of multi-phase style simulations. And we were just discussing the different ways that are commonly used. And we discussed the basics of level set methods. My group uses them sometimes. Dr. Stewart's group uses them all the time. Tom Jackson uses them all the time. So these are very common techniques, and they have their pros and cons. And they're, of all the methods, they're probably the most they are probably the most flexible, in that you can divide your you can divide the domain into an arbitrary number of regions, and in each of those regions you can do whatever you want. You just need to be able to basically get the flow in the different regions to basically interact properly. But then level set methods are very, very flexible, but they do have mass loss just due to just numerical rounding of basically sharp pointy parts. And even if your simulation doesn't start with a sharp pointy edge, if you have a droplet breakup and shatter into a billion smaller droplets, you will have sharp under-resolved things unless you have insane computational resolution that is not practical today, even on the largest supercomputers. And so maybe in 10, 20 years, you will be able to resolve everything, but not for like one droplet that's shattering into a billion smaller droplets, but not now. Okay, and a other method that's used not very often. There are a couple groups that use this, but they're called front tracking. And so where level set methods evolve an interface, what front tracking does is you sort of have this generic little blobby thing, and then you seed it with you seed the surface with a bunch of marker points. And then instead of evolving a function for the interface as you would with a level set method, you evolve the position of basically all of these points, and that's how front tracking works. And then, but what makes front tracking difficult is that the fact that you need to have a connectivity list, is that you need to know that this point here is connected to this point here. But what can happen is, if over time this blobby shape splits into two, you now need to dynamically adjust your algorithm so that it can sense that it's split into two, and the split is right here. And so the neighbor of this marker particle used to be this one over here, but now it's this one over here. And so there are all these connectivity, the sort of dynamic, the dynamic reforming of all those points. If basically these two come together and join, you need to change the connectivity list of all the points. And of course, this is in 2D, but in 3D, this becomes very complicated really fast. And there are only a few people that I know that have codes that do this. And they're almost never compressible, although I think Gitrar has one, but they're very, very complicated to implement because of the logic that is needed to track the interfaces, connect the points. And for those of you who've done meshing before, on 3D, this is a surface triangulation that they have to do to get all the surface stuff correct. Because of all that extra stuff that you have to do, it is extremely accurate. You get very good curvatures with it, so you get very good surface tensions, and it's essentially it's almost mass conserving, but it's hardly used because it is very expensive and it's difficult to implement. And also the details of how a droplet breaks up is somewhat dependent on the coder's implementation of their logic of deciding deciding when deciding who your neighbor point is. And so there is some arbitrariness to it too. But if they do a good enough job with it, the results from basically one group to another group are very comparable and almost the same. But there is a little bit of arbitrariness associated with their algorithm to decide when when a droplet splits into two smaller droplets, or if two droplets merges, that they need to make a decision on the connectivity list of all these particles. Okay, so does this concept make sense? Okay, and then a third method that's used quite a bit, especially for incompressible flows, is called the volume of fluid method. And I'm going to spend a lot of time discussing the equations for this, because they're the same equations that are solved for a whole lot of multi-phase flows. It's just the volume of fluid method, or VOF, is nothing more than a special algorithm for solving those equations. And so the starting point for VOF methods is we need to derive the governing equations for a multi-phase, for a resolved multi-phase flow. So you can derive those equations the same way you do the normal Navier-Stokes equations. You can use a Reynolds transport theorem, although it does need to be modified to account for the presence of the fact that in your control volume, where you'd be using the Reynolds transport theorem, you now have multiple phases. So you have gas over here and liquid over here. And so when we're deriving these governing equations, we're going to use a finite control volume approach, or I'm going to give the highlights of it. I'm not going to go through it. It takes forever. Then we're just going to assume that the width of the computational cell is delta x and the height is delta y, and the derivations and all that stuff are straightforward and extend easily to 3D, albeit with a lot more work. And so the idea here is we have our control volume and we divide it into gas and liquid subdomains. And so basically we're going to, instead of using the conservation laws on the entire control volume, when we derive conservation laws for the gas, we are only going to consider the gas portion of the gas portion of the control volume. And then when we want to derive conservation of, say, mass for the liquid, we are only going to consider the liquid portion of the control volume. And so we're basically splitting each control volume into multiple pieces. Okay, and so then before we get going, we need to define a volume fraction alpha. I call this alpha. I think Bala's group tends to call this phi. You see alpha or phi being used quite a bit, so just look for those. Basically, those two symbols in these types of flows. They normally mean the same thing. Okay, and now the sort of liquid volume fraction is just the volume of the liquid in this computational cell divided by divided by the total volume of this computational cell. So it's just the volume of the liquid divided by the total volume, and that's how it's defined. And then, of course, if you have two phases, say gas and liquid, then the volume fraction of the gas is just 1 minus the volume fraction of the liquid, because again, it's defined to be a fraction. So the sum of alpha k equals 1, where k is a number of phases. Because I could repeat, I could also do a control volume analysis where I have an arbitrary number of phases inside of this control volume. I could have some solid over here. I could have some small droplets over here. And so you can have an arbitrary number of phases, and this procedure still works. Okay. So,
Professor,
yeah.
About the number of phases, does that mean K is limited to 3 or I guess 4 for plasma, or is it like, can you have like 6 phases in there?
You can have an arbitrary number of phases.
So what does that mean if it's like 7 phases?
You could consider a phase. I'm using it in the loose general term. You could use a phase as oil and water if you and that's a very common thing that's done, is that between the oil and water they don't mix, right?
Hmm.
And so if you want to do a multi-phase flow simulation of oil and water, you treat them as separate phases.
Oh, okay. Okay.
Yep. And then also if you're working with solid mechanics, you can have you can have different phase transitions in the solid, like say a like alpha crystalline phase to a beta crystalline phase, and people need to worry about that sometimes.
Oh,
For Go ahead.
oh, I was just saying, okay, that so that different materials, they all just count as different phases as well. It's not just all solids, all liquids.
Yep, yep. And so and and basically if you have say if you have in reality, if you wanted to, you could treat each species of a gas as their own phase, and then apply phase change between those phases to mimic a chemical reaction. I don't know why you do that, but in principle, you could define them as different phases and then do it that way. That is the sort of silly way to do it, but I've never heard of anybody doing that. Um, and so basically, after you work with these equations a bit, you'll start to see when to define two different things as species in the same phase, and basically when to define two different substances as different phases. And that just takes nothing more than experience.
Okay, that makes sense. Thank you.
I shouldn't say nothing more. It takes a lot of experience to sort of know when to do that. And because of that, different people will sometimes solve the same flow different ways, basically for that. And so this multi-phase flow stuff, especially when you deal with combustion, it's kind of the wild, wild west. There's still arguments over which equations to solve for some things. So which then that makes it kind of fun because there's a lot of nice theoretical work to do. But anyways, we're just doing the basics here. Okay, so there's a volume fraction, and then intuitively the sum of all the volume fractions have to be equal to 1 if you have an arbitrary number of phases. And so you're going to do a control volume analysis on this, on gas, and for the derivation, we're just going to assume two phases, gas and liquid, but this extends straightforwardly to an arbitrary number of phases. Okay, and so we're going to do a CV analysis. And so I'm going to do conservation of mass just for the gas. And so I'm going to take this control volume here, and I'm going to simplify the surface of the liquid so that basically so I can draw it easier. So I just say that the liquid is this little triangle here, but it can be any arbitrary shape. And the gas is this region right here. And so since we're conserving mass just for the gas, we have mass flow going out, but only on this little piece here. We have mass flow going out through the top. In this case, the way I have it drawn, we have the entire surface here. We have mass flow going in and mass flow going in through the bottom. And then also, if there's phase change, we also have mass flow from the gas phase point of view, basically coming in from basically coming in from this gas liquid portion inside of the control volume. Okay, and so this is from phase change. And so this model so we already have this extra little edge here that you need to consider for these types of flows that you don't in the standard single phase governing equations. Now, what we're going to assume, and I think I have it written over here, is we're going to assume that the amount of area that is not liquid at each edge of the control volume is equal to the gas phase volume fraction. And so that is an assumption. It's a common assumption. Everybody makes it without sort of realizing that they're making it. Is that you're assuming that the area fraction equals the volume fraction. Okay, and so I think if you have spheres, statistically that's true, but say you're dealing with gun propellants and they have a bunch of little cylinders or cylinders with holes in them, then, you know, that, I mean, people use it anyways because there's really no other way of doing it. But that can get kind of, that can get kind of iffy if in the charge cartridge, all of the grains are aligned in sort of one direction, then that gets a bit iffy, but no one that I know of, even at ARL, accounts for things like that. It gets too, there's just simply too much to keep track of. Okay, so we are assuming that the fraction of the area where the gas can flow on this side of the control volume is just simply the sort of gas phase volume fraction. Okay, so that is an assumption, and of course that is at this edge over here, and then we repeat the same. So basically, the total mass flow going through this little piece here would just be the gas phase velocity times or the gas phase velocity times the gas phase density, and that would be the mass flow rate through the entire section here, but most of it is blocked off over here, and so only this little piece is basically where the gas is flowing through, and that is the gas phase volume fraction. And this looks like I'm doing a bunch of hand wavy things, but there's a very rigorous RTT or sort of Reynolds transport theorem way of doing this. And all this stuff sort of comes out of that. I'm sort of doing it in a more intuitive type of approach here for the sake of time, because to properly derive that RTT and things like that takes time, and time that we don't have. And so anyways, so now we have all of our mass flow rates going through the control surface. And so we can apply the Reynolds transport theorem, the sort of normal one, to our sort of strangely shaped control volume here. Okay, and then again, we are only on the gas phase portion of the CV, and so we can basically integrate the mass. So then the integral over the control volume of rho g dv gas is just basically rho g times the gas phase times the gas phase volume fraction. Well, recall that alpha g is defined to be Vg over V. So this means that Vg equals alpha g times V. And so the so then this integral just becomes the gas phase density times the volume fraction times the total volume in our control volume. Okay. And so then we got these edge terms here. And so if we're going to integrate over the area of a face of our control volume, we have the integral of rho g Vg dot n hat dA. And again, this is just for the gas phase portion. And so this is just like what you did in undergrad fluid mechanics, where you have rho g V dot at the face times the flow area. And the flow area here, again, we are assuming that the flow area is that the area fraction, that is the area of the gas divided by the area of the total area of that face of our control volume, is equal to the volume fraction of the gas. Turn it off. Okay, and so, oops, wrong one. And so our mass flow rate through the general mass flow rate through any face is just rho g times the face area times the gas phase volume fraction, because again, we are assuming that the area fraction is equal to the volume fraction. That is an assumption again, times V dot n hat at that face. So all stuff that you've seen from fluid mechanics, we just need to be very careful to account for the volume fraction. Okay, then we do a standard. Now we have all these mass fluxes here. We know how to basically do. I basically wrote the answer right here, but you can also do a standard RTT for conservation of mass and get the same result. And so we do our standard, type of analysis. We basically walk around all the edges of the control volume and account for all the, and then account for all of the different, all of the different mass flow rates, and then take the limit as delta x and delta y. And if you're in 3D, delta z, go to 0. Okay, so other than accounting for the area fractions and volume fractions, it's almost the same as you did it before. And when you do that, we have our governing equation for gas phase mass is just the time rate change of gas phase mass, which is the volume fraction times the density of the gas times the divergence of the volume fraction times the gas phase density times the gas phase velocity times the total amount of mass flow that is going through the surface here, divided by the volume. And I'm just going to call this m dot triple prime g. And again, I'm sort of adopting heat transfer notation, where basically the triple prime means it's a quantity that is per unit volume. And so this here is actually representative of your phase change model. Okay, so are there any questions with this? So it's essentially the same. So this is gas phase conservation of mass. Okay, so this is essentially the same as the standard conservation of mass, with the exception that the gas phase density in the two terms are weighted by the volume fraction of the gas. And of course, due to phase change, you have mass exchange. You have mass going into, you have mass you can have mass from the liquid side changing phase and going into the mass of the gas phase side. And so that is what this term means here. Okay. And then of course, the specific model for the phase change is dependent on what you're doing. You could have a propellant, so you use a St. Robert's law type thing. You could have a liquid that's evaporating. You could have droplets that are burning, particles that are burning, all sorts of things. And so this starts to get very, very model specific. And then we can repeat the same procedure that we did for the gas, but now we're on the liquid portion of the control volume, which is down here. And then if you do that, you wind up with the exact same thing, except for if you were to do the control volume for the liquid, it would be this piece here. And instead of gaining mass at the interface due to phase change, this is now mass that is leaving the liquid side of the control volume. Okay, so if you do that, you have essentially the same thing for the liquid phase mass, except for you have minus the mass that is lost at the gas liquid interface, and because basically a gain to the gas is a loss to the liquid. And then in general, you could call this you could call this m dot triple prime L, which by conservation of mass, overall conservation of mass must be m dot triple prime G. And basically what I mean by overall conservation of mass is if instead I did the entire control volume here and accounted for both the, and I simultaneously derived a conservation law for the gas and liquid, this edge here would be inside of that control volume. And so basically, if you were to account for the total mass, gas and the liquid together in one equation, I'm not going to show it, but you wind up with the standard conservation of mass. And this extra sort of source term for phase change is not present because any gain to the gas is a loss to the liquid. And since basically both are internal to the overall control volume, it's just not, it's, you know, it's simply not there. Okay. And so are there any other, are there any questions?
Yeah, I have a question. So are we looking at the entire volume here, or is this just one chunk, one cell we're looking at?
This is just, no, this is an infinitesimal control volume.
Okay, so I was just thinking about like implementing this on a computer, if that's kind of where we're going, like, yeah, resolving this cell. Aren't we going to get to some point where the computer, it's like, I have a mixed cell here. How do I handle that? I'm not resolving that cell any smaller.
Yeah,
Right.
we will discuss that a bit, but that's a computational issue.
Okay,
Because basically you use, basically this does handle mixed cells and non-mixed cells. Basically, this here is one computational cell. So in your code, it would say that there is a mixture of gas and liquid in this one computational cell, right?
right.
But for the purposes of deriving the equations, we need to separate them and
Okay.
then derive the governing equations that are in turn solved by the computer. Does that make sense?
Yeah, it just seems like we're resolving that cell finer than we're telling the computer, like, how does it know? We can give it the fraction of material of each phase that's in there, but then picking exactly where that material exists, meaning it's refining that cell even further within
Yeah, but that's
cell.
just for the derivation of the equations. You'll find that basically what you're getting at is that, so I guess if you derive these equations, I could do the exact same derivation, but instead I could have a bunch of little droplets, right? And my gas phase control volume looks like, it basically looks like Swiss cheese, because I have all these little solid particles that are taking up volume, right? That is conceptually, that is a completely different type of flow than a nicely resolved gas liquid flow, right?
Right.
Okay. I guarantee you, if you do the control volume analysis properly with this one and this one, the governing equations themselves for conservation of mass and momentum and energy are the same. They are identical.
That makes sense. And it seems like with the one with the Swiss cheese, I could almost give it like some stochastic representation of where those things exist, where it seems like on the liquid gas one, I have to, it's specifically existing in the lower right corner of the cell.
No, well, I mean, these are just, in reality, with numerics, this is going to be smeared out. This is just for the basic derivation. And you could apply and also when you use the Eulerian approach, if you're dealing with Lagrangian droplets, there are things that are physically Lagrangian. When you basically deal with the multiphase flow equations in Eulerian form, you're basically just taking all the properties of all the particles that are in that control volume and basically averaging them out. Now, where this occurs, or basically where like the big difference is, even though the governing equations themselves for a Eulerian multiphase flow equation for this case, in this case, even though they are identical, what's different is how you interpret the results of that flow. And then also all the models that you use for, say, momentum transfer, heat transfer, things like that between the different phases changes, and even the numerical algorithms change a bit, is that you want to keep this interface as sharp as possible. And so you want to use special algorithms to basically keep this sharp. Like CTH, as I know you know about, has special algorithms to keep the interfaces very sharp. And so CTH works is horrible at things that mix, because it doesn't allow them to mix. And so basically your interpretation as to what the material are, basically what the materials are, whether they are dispersed or they are continuous, which is what the big sort of groupings are, has a big influence on your choice of the phase change model, and basically all of the other stuff. Okay.
Okay. Yeah. Thank you.
Yep. Okay. So then you can repeat the same for momentum. And I'm not going to go through everything, but I'm going to go through the control volume, and I'm just going to go over one special term. And that is, in this multi-phase flow stuff, it is the most evil, horrible term that there is. It doesn't look horrible, but it is horrible. It's called the Nozzling term. So if you're doing the gas phase, a control volume on the gas phase, and you want to sum up all the pressure forces, you have pressure pushing over here, pressure pushing over here, pressure pushing over here, and pressure pushing over here. But also there is some interfacial pressure, P-int, from the liquid that is also pushing on the gas, and then the same interfacial from the gas that is also pushing on the liquid. So again, this is one of those interfacial things that is not present if you do an entire control volume, but then that doesn't really allow you to separate the phases in a rigorous fashion. So when you sum the pressure forces, you have, again, the pressure on the bottom, the pressure on the side, the pressure on the top, and the pressure on the right. But you also have this extra pressure that is pushing on the gas liquid interface. And yes, if I have a dispersed flow where I have a bunch of little particles, I have a very similar interfacial pressure term, because in terms of the governing equations themselves, how the liquid mass is sort of distributed within a tiny control volume makes no difference. Okay, and so that's sort of why we use this approach, derive the governing equations, and then put them to the computers. We need to know what equations to solve. Okay, and so now if we just look at the pressure forces in the sort of x direction here, is that we would have a pressure pushing over here and a pressure pushing over on basically this gas phase portion. But also we have an x direction of pressure over here that is pushing on this portion of the control volume. And so now we need to sort of figure out what that is. And this is hand wavy. It's not the super rigorous way of doing that. But basically basically we just want the x component of this interfacial pressure force. And so to do that, really what it turns out to be is it's the interfacial pressure times this, basically times this height here. And you can show that that height there is related to the sort of width of the control volume times the gradient times the gradient in the x direction of the control volume, or I mean of the liquid volume fraction here. Okay, so you can sort of just see that almost the way I have it drawn in this sort of cartoony, like triangular portion on the very right edge, as sort of in this cartoony way. You can sort of see it geometrically, which is why when I derive the equations, I don't like the Swiss cheese approach. These terms that pop out seem like miracles, but if you draw it like this, then they seem a bit more intuitive. Okay, and so then this sort of net pressure force in the x direction would be minus P-int times this gradient here. And then basically, if you extend that to multi-d, take the limit as delta x goes to 0, all that good stuff, what you wind up with is the net pressure force would be on this face is this interfacial pressure times the gradient of the volume fraction of that phase. Again, you need to do a more formalized Reynolds transport theorem analysis to very formally derive that term, but it's there. It's also there the other way. There's another way that you can derive the multi-phase flow equations too for the gas, is you can do almost like what Vincent suggested earlier, is basically you take the sort of gas phase, you take a gas phase governing equations, and then you basically apply sort of a Gaussian sort of stochastic field around the particles and take various limits. And when you do that, you also wind up with the gas phase flow equations modified by the presence of the particles. Jesse Capilasa-Taro, I don't know how to say his name, did that in a very recent paper, very formally for compressible flows, and you wind up with the same sort of thing. And so I know there are some fights over which multi-phase flow equation to solve, but if you can derive the same equations basically 3 or 4 different ways, then you know they tend to be on very good theoretical grounding. But anyways, so because of this interfacial pressure here, we have this goofy extra force here, P int grad alpha G. And after I just write what the governing equation is for the gas phase, and then I will explain what that term is.
I've got a quick question real quick.
Yeah.
So just for continuity's sake, I know at some point they'd probably end up being equal, but in the graphic it's negative del x d alpha L, and then on the right it's d alpha G. Are they pretty much the same?
Let's see. I might have been a bit loosey-goosey here. But if there are 2 phases, you can show that grad alpha G equals minus grad alpha L.
Okay, that's what I was going to say. I just wanted to make sure.
Yeah, because remember the sum of alpha K equals 1. That means that the grad of, oops, that's a bad sum. The grad of the sum of alpha K equals 0, right? Because the gradient of 1 is 0, which means the sum of the grad of the alpha Ks is equal to 0.
Yeah.
And if you have 2 phases, then basically the sort of gradients are equal and opposite.
That makes sense.
Yep. Okay. So anyways, you go through a more rigorous analysis, and the governing equation that you solve for multi-phase flow for momentum for the gas phase is this equation here. Again, most terms are just modified by are just the same as the same as the normal momentum equation, with the exception that you have all these extra terms here, that most terms are weighted by the gas phase volume fraction, and you do have these extra terms here. And actually, I should put F. Okay. Add an extra term there. Okay. And so this here is resulting from this interfacial pressure term here, and it's called a Nozzling term. And the reason it's called a Nozzling term is because it is analogous to the PDA term in nozzle flow. Right, so you could imagine that if I had this control volume and gas flowing through it, like basically think of this as like a channel. Right, so if I had a channel and I had flow going through this channel, like that, and I had steady flow going through this channel, you know that intuitively, depending on the Mach number and things like that, is that the flow will speed up. Say it's subsonic, the sort of flow will speed up as it goes sort of through this little nozzle here. Well, so when you describe that, the term that does that acceleration in the 1D nozzle flow equations is the PDA term. Okay, and so if you look at this P int grad alpha G, it really comes from a sort of pressure times a differential area, which is basically what this is right here. Okay, and so they are very analogous, and that makes intuitive sense. That you can think of, okay, so say I'm going to have I'm going to have a cluster of particles over here, or some sort of solid, or some sort of liquid. If I play a DD of your choosing and I fix that liquid and solid in place, then as far as the gas is concerned, it's just a solid object that the gas has to go around, right? And so the gas will have to the gas will have to accelerate as it goes over and around that obstacle. Okay, and so that sort of gives rise intuitively to what this nozzling term is, and this nozzling term is crazy evil. It looks like it looks like a simple term to add to solve, but for compressible flows, this term here is evil, and if you do a formalized wave speed analysis, this term can make your equations lose what's called hyperbolicity. And basically in this context, what that means is that if you were to compute the sort of sound speed for this multi-phase mixture, is that some of the wave speeds would they start to have complex values, and then you can trace the source of that usually to this interfacial pressure sort of nozzling term here. So this is evil, but it is necessary to include that term. Otherwise, things are completely wrong. For our blast stuff that we do, if we don't include this, we get crazy results. Okay. So then also, we have sort of an interfacial stress term dotted with the gradient of the volume fraction. This here is basically just an interfacial shear stress. So you could have shear stress basically occurring. Not many people I know actually include that term, but sort of heuristically, that if you have a separated gas liquid flow, you could have some shear stress going on at the interface. And then also you have momentum exchange due to phase change. That is, if I have gas over here and there is phase change, well, there is not only is there mass loss to the liquid, but there is a loss of momentum too. And so that loss of inertia to the sort of liquid is given to the gas. And then that is what this term represents. Then also you have other sources, you have other forces that can occur basically on the, that can occur on the gas. And those could be buoyancy. They could also, if you have particles, they could also be drag forces too. I sort of lump them all into one. And so these equation, even though I sort of derived it for this sort of specific control volume shape, the actual goings on the inside of the control volume, whether they're dispersed particles or not, makes no difference. If you account for everything, the overall governing equations are the same. Okay. And so, except for now, we have an interfacial pressure we need to define, and sort of an interfacial shear stress that we need to find, and an interfacial velocity that we need to define how to basically account for the loss of momentum from the liquid. And then also extra sources like say drag forces. If you're dealing with, if your flow is actually a separated gas liquid flow, this here can be 0, but if there are particles, you need to account for drag forces and other things. Okay, so then you can do the same thing for the liquid. I'm gonna skip that, but you wind up with almost the same equation, except for the sort of the subscript G's for gas. I know subscript L's for liquid, and yeah. And so now when you do this, the interfacial pressure and velocity, they need to be chosen, and they are quite often P-int and V-int are normally chosen to be the gas phase pressure and the liquid velocity. Okay, and so those are very common choices. Sometimes you see people, because there really is no good rigorous theory for like picking one over the other. I've seen people use V-int as the average of the gas phase velocity and the liquid velocity. Okay, and then the interfacial shear stress is often neglected. There may be some things that have models for that, but I'm unaware of them. It's often neglected because I've never heard of anybody ever really accounting for that. Okay. So are there any questions with momentum? Okay, so you can see that just due to the sort of presence of the blockage of the flow area by the other phases, and basically accounting for basically all the interfacial areas, either this piece here or the edges of basically all the particles, all the mass, momentum, energy exchanges, the equations start getting pretty complicated. There are a whole lot of extra terms. And for some types of flows, some terms may be present, and for other types of flows, they may not be present. So these are just very general equations, okay? So now there's species mass. And so here we have the mass of species I in phase K. So this could be, the liquid could have different species. You could have a mixture of alcohol and water. And you want to study the combustion of that, you would have two different species in here. And then in the gas, you could have a sort of reacting flow, and you need a way to keep track of all of those species. And so that's a much more straightforward analysis than momentum. So that's just a natural extension of what we've been talking about, except for now you have homogeneous chemical reactions occurring inside of the gas phase portion. And so that's just the normal mass rate of production, but it's weighted by the volume fraction of phase K, because again, only this portion of the control volume is where the gas phase chemical reactions can possibly occur. And then also you have gas species coming in due to phase change operations, and that's omega dot K for heterogeneous. Okay, and then also you have basically the transport of species out due to convection and also due to species diffusion. Okay, so again, this looks almost the same as it did before, with the exception again of the volume fraction and the heterogeneous species that are produced by phase change. Okay.
Can I ask a quick question, just to make sure I'm understanding?
Yep.
So if instead we were looking at a bunch of particles in this cell, this gas mixture with particles, you could essentially arrange all your gas particles uniformly such that the gradient of the volume fraction is 0, right? That it doesn't change with respect to X.
In what context is this? Is this for the Nozzling term or?
Yeah, I was just thinking for the Nozzling term, couldn't I make that go away if I had a uniform distribution of particles so that my volume fraction didn't change with X?
You could, but then the entire spatial domain would have a uniform volume fraction.
Right.
So you could think of that that conceptually, that when you derive the governing equations, it's not one control volume in isolation. It's a bunch of infinitesimally small ones. So you could assume that the volume fraction is constant in one control volume, but say the volume fraction actually looks something like this, right? That there's some sort of step change. You can choose your control volume here and control volume here, and there's going to be a step change in the volume fraction at that interface. And so basically, you're still going to have that. You're still going to have that Nozzling term, or you could choose your control volume to be here. So you're always going to have. So
gotcha. Okay.
So in a sense, we derive the governing equations in the most general format possible, and then you just cross out the terms that you need or don't need for your given application. Does that make sense?
Yes, it does.
So there's a whole lot of arrows and everything going on here, and I'm not going to draw one for the energy because that one gets crazy. But there's a whole lot of arrows here because I'm just deriving them in a very general way. And then when you work with these, if you work with Eulerian modeling for particles, you just cross out the terms that you basically cross out the terms that don't make physical sense for the particles, like the interfacial shear stress. That term makes no sense for particles, at least that I can think of. Okay, because I guess that term would be accounted for by drag anyways. Okay, but anyways, so we go back to the species mass equation. We have our speed. Oops, whoa, that was not good. We have the species mass here, and we account for that. And when we do the CV analysis and let delta x, delta y go to 0, all that stuff, we have this equation here, where again it's the standard species mass equation, except for of this weighting by the volume fraction in front of all the terms, including the homogeneous chemical reaction, and we have this heterogeneous reaction term here, and you can prove that m dot triple prime k equals the sum over I equals 1 to the number of species in phase k of omega dot ki het. Okay, so that's just what conservation of mass requires. And so the other sort of implicit difficulty, especially when you deal with multi-phase combustion, is the fact that you start having massive bookkeeping problems. Is because you can have multiple phases, you can have different species within all of those phases. So not only do the governing equations become more difficult, but even just the bookkeeping and keeping track of what species is in what phase and ordering everything and all that stuff, that also becomes quite complicated. Okay, and then I'm just going to write what the conservation of energy is. You can see that it takes, with granted my handwriting is kind of large, but it takes 4 lines. Oops, and this goes over here. It takes 4 lines to write, where this is the total energy. So you could say E equals E plus 1/2 V dot V. And so we have total energy. Again, these are all modified by all weighted by the sort of volume fraction. Now, there's a very interesting term here that pops out. And this here, this PK, the pressure of phase K times the change of volume fraction of phase K, that is due to PDV work. So you could imagine if I have a control volume and I have a single vaporizing droplet. Well, as this droplet shrinks, I'm going to have pressure forces that are pushing on that droplet as it shrinks. And so to the gas, so basically as the volume of the gas changes, there is pressure work being done basically as that interface moves. And so this here is actually PDV work. Okay, and so basically this accounts for things like that. And then also you could have a change of volume just to, you also have a very similar thing that the single droplet here can actually be transported out, and then as it's moving out of the control volume, like say it's over here, well, there is a volume fraction that is changing as the particle leaves, and there are pressure forces that are pushing that are basically pushing on that surface as it is moving out. So whether it's basically whether the volume fraction is changing just due to particles entering and leaving the control volume or phase change, there is PDV work that is associated with that. Okay, then you have this extra term here. That's just due to the energy transferred due to phase change. So basically, when you vaporize, say, the liquid, not only does whatchamacallit, basically not only does that transfer mass and momentum, but also it transfers the energy that is being transferred with it. There's interfacial heat transfer, interfacial work, basically work due to other forces, other heat transfer, and other work terms. And so, so this equation is a gigantic mess, and all of these terms here, and actually this one here is wrong. It's interface, P-interface here, and a lot of these terms need to be modeled and are often neglected because in a lot of times there is no model for them. Okay, and so those are the governing equations for a very general multi-phase flow for phase. You can easily extend this to multiple phases. And then now we are going to simplify them basically next time to the so-called 5-equation model that's used in VOF modeling and a lot of other things. And then we will discuss other forms, what is appropriate for say a flow of rigid particles, and then the so-called Bernoulli equations, which are used a lot in high explosives, and then we'll just discuss some applications because teaching you guys again, there could have an entire class just working with these equations here. And so can only sort of, and also the numerics of them get very complicated. But that's a completely different class. So are there any questions?
So this volume of fluid method is the most common method that's currently used, or?
No, it's used, the VOF method is a special algorithm for that. I sort of just list it as that. But what is actually becoming common are these VOF related methods. And basically the VOF related methods just have a different algorithm, an easier algorithm for basically handling the volume fraction. Because one thing I need to get into here that we will discuss is that we have extra unknowns. Is that basically we have conservation of mass, momentum, and energy. So we could get densities, velocities, and temperatures, say, from those 3 equations, but we have no condition to get the extra volume fractions. And so these equations are actually incomplete. And so you need to make an assumption as to how to get the volume fraction. And that's where a lot of the difference is for the different for the different models. And there's a lot of debate. Okay, but yeah. And so the VOF method is used a lot, and it's used a lot in incompressible flows. I mean, a lot. But for compressible flows, the VOF method is kind of difficult to implement, and you don't see it implemented that often. And so they tend to use these VOF related methods. And actually, Braden is using one of them for his compressible solid mechanics stuff. Is a VOF related method. Okay, and so I will just discuss in a hand wavy fashion as to the difference between these 2 methods next time. Okay, and first we need to deal with what we do with that extra piece of information that we need to get the volume fractions, because that also dictates what type of flow that basically you are solving. Even though conservation of mass, momentum, and the energy are the same, there are differences into how you handle the volume fraction. And then basically in that massively dictates which form of the multi-phase flow equations are appropriate for which type of flow. And so so again, these are very generic, but you need to make some assumptions and simplify them down to something that you can solve, because I don't know of any person that accounts for all of these things that are listed for conservation of energy. Because there are a lot of terms. They're not always important for various flows, and even if they are, and even if they are, some of them you don't know exactly what to do with, like this interfacial shear stress term. If you have a truly subgrid gas liquid surface, there's really not that good of a way of dealing with that I know of. There's some hand wavy things that are done sometimes, but this stuff gets really complicated. But that's part of what makes it fun, is that you get used to it, and you get used to, and when you work with this area, you get used to manipulating the governing equations, making assumptions, crossing out terms, And also making modeling sacrifices is because you don't know what something is and you have no choice, whether it's good or bad, to basically neglect a term because you have no idea what to do with it. And so that's not uncommon in this area. Sorry, I've been blabbing on for 10 extra minutes. Sorry about that. Are there any other questions?